Good day, students. In this clip, we're going to be reviewing some problems on graphs of trig functions. So let's take a look at question number 1. So it says, give the amplitude and period of the graph. So we have this graph below. If you examine this closely, what kind of trig function does this look like? To do a real quick review, remember your sine function looks like an S. If it's positive, the sign goes up like this. That's one period. If it's negative, it goes in the other direction like this. And your cosine function looks like a cup. So one period of your cosine function, if it's positive cosine, looks something like this. So let's write this. This is positive sine, and the red one is negative sine. And then for this one, you see this cup orientation. That is the positive cosine. The positive cosine starts from the maximum. Okay? And the negative cosine starts from the minimum and goes in the opposite direction like that. So that is a negative cosine. Okay, let's take a look at this graph. What does this look like? Looks like the curve starting from the maximum. So this is a positive cosine function. Okay? Now it asks for the amplitude. The amplitude is a displacement from the center to the max or center to the min. Okay? So this is a central position. The midpoint from the tip from the maximum points to the minimum points. This is the central position. Center. And we have the maximum, which is where all the peaks stop at. This is the maximum displacement from the central position. And this is the minimum displacement. Okay? So we have our center, max, and min. Now note, the amplitude is not a displacement from the min to the max. It's a displacement from the center to the max or min. So I can either compute this distance from here to here, or I can compute this distance from here to here. Okay? So how many units displacement are there from the center to the maximum or from the center to the min? That will tell us what our amplitude is. And we can clearly see that it's 4. I kind of covered it up a little bit. So this is 4 units. Okay, so that's our amplitude. Now to calculate our period, there are different ways we can calculate our period. One complete cycle is a period. So we had the maximum here. From this maximum to the next maximum on this graph, that will be our complete period. So we can go from maximum to maximum. That length will tell you the period. Or you can go from minimum to minimum. That length will tell you the period also. Okay, so let's do from max to max. From max to max, we can clearly see that the length from this max to this max is 4 units. No, I'm sorry, it's 8 pi units. From here to here, it's 8 pi units. So the period is 8 pi. All right, so let's write this down. The amplitude we found before, from the center to the maximum, is 4 units. And the period from max to max is from 0 to 8 pi is 8 pi units long. So we can clearly see that our answer is option letter D. Okay, let's take a look at number 2. We are asked to sketch the graph of these 3 functions and basically say what their similarities and differences are. All right, so let's start with function number 1. We are going to be graphing 3 cosine functions. So let's start with the first one. But before we do that, let's write down the general form for the equation of trig functions. So we have y is equal to a cosine bracket b x minus h plus k. Okay, so that's what we're going to be using to generate the graph of this function. So let's start with the first one. We have y. I'm going to write this function in this format. Okay, The coefficient of cosine is 1, y equals 1 cosine. The coefficient of the x is 1, so we have bracket 1 times x minus h. Let's change the h to a 0, since we're not subtracting anything from the x, so x minus 0 plus 0. Okay, if you have this x by itself, nothing being added to it, you have 0 and 0 here. Okay, now let's determine what the new origin is, where our graph is going to be centered. New origin is going to be 0, 0. So we can see that our phase shift is 0 and our vertical shift is 0. Let's figure out what our period is. Our period is 2 pi over b. 2 pi over b. In this problem, b equals 1. So we have 2 pi equals our period. And that tells us that 4 ticks is going to be equal to 2 pi. Okay? If you notice in this calibration we are using degrees, so if we want to write this in degrees, we're going to have 4 ticks equals, pi is 180, so 2 pi is 360 degrees. Alright, so I think that's enough information to graph this function. Oh yeah, we also need our amplitude. Our amplitude is A. Amplitude is the absolute value of A, so we're going to be computing the absolute value of 1, which equals 1. Alright, now let's go ahead and graph the function. So we are starting from 0, 0, and our amplitude is 1, so let's graph a 1 here. That's how high our function is going to go, and then it's going to go as low as 1, like that. Okay, so 4 ticks is equal to 360 degrees, so let's go ahead and do our calibration. So we have 4 ticks is equal to 360. So we have, if we break 360 into 4, we'll end up with these 4 ticks here. 90, 180, 270, and 360. So we have 360 divided by 4 is 90 degrees. Alright, so let's go ahead and graph the cosine function. We know that the cosine looks like the cups, so let's graph that. I'll graph the first one in red. So we have, it starts from the maximum, goes to the center, minimum, center, and right back to the maximum. Okay, so that's what our cosine function looks like. Let's connect the dots. So first, just a sketch. So something like that, and it ends there. Okay, let's graph the second one. We have function number 1 graphed. Now let's graph function number 2. Let me do the entire thing in green. So function 2, let's write y equals cosine 4x in the general form right here. So it's going to be y equals 1 cosine. You notice that b is 4 now, so 4 times x minus, nothing is being subtracted from x, so 0. Nothing is being added to the entire function, so it's plus 0. Okay, let's find our new origin. New origin is going to be the opposite of the letter next to x, which is 0, and then the number that's been added or subtracted from this term, which is 0 also. Our period is going to be 2 pi, or let's use 360 this time. 360 and 2 pi are the same thing. So 360 over b is 4, so 360 over 4 is going to be equal to 90. Alright? And our, so that tells us that for our calibration, 4 ticks is equal to 90. Alright, how about our amplitude? Amplitude is the value of A. In this problem, we can clearly see that A is 1. That's the coefficient of cosine. So we have absolute value of 1 equals 1. So that's enough information to graph. Let's go ahead and graph the function. We're still graphing cosine. Let's do the first calibration. 4 tick marks equals 90, so we have to divide this 90-degree region into 4. So the quickest way to do it, we split it down the center like this into 2 halves, and then go on to split the halves you created into another set of halves. Okay, so split this down the center like this, and split that down the center like that. Okay? Alright, so we can graph it there. So starting from the max, we have max, center, min, center, max. That's one complete period. We can see that it is much smaller than the other one. It has a much compressed period. So we graph it like that, and that pattern basically continues for the entire region. Okay. All right, so that's our second function right there, function number 2. Now let's graph function 3 and see if we can make a comparison. So for function 3, we have y equals 4 cosine x. Now let's write this function in this general format here. So we have y equals 4, that's now a cosine. The coefficient of x is 1, x minus 0 plus 0, because nothing is being added or subtracted to the x, and nothing is being added to this whole term right here. Now let's find our new origin. New origin is 0, 0. Opposite of the number next to x is the x coordinate, and then the other number is the y coordinate. Our period is 2 pi over b, or we can use 360 is the same thing as 2 pi radians, 360 over b, which is 1. So that's going to give us 360 degrees. So that tells us that 4 ticks is equal to 360 degrees. Okay, so each tick will be 90 degrees. And lastly, we need our amplitude. Our amplitude is the value of absolute value of A. So absolute value of 4 is 4 units. So we're going to have a displacement of 4 units up and down from the central position. Okay. All right, we have all the information we need. Let's go ahead and graph it. Our maximum is going to be at 4 this time because of the amplitude of 4. And our minimum is going to be at negative 4. Calibration will be the same as the first graph we drew, function number 1. So 4 tick marks, 1, 2, 3, 4. 4 tick marks being equal to 360 degrees, as we can see here. We are still graphing our standard cosine function, so we start from the max, center, min, center, max, and then we connect the dots. Okay. So it goes like that, like that, like that, then like that. Okay? Okay, let's go ahead and compare the graphs, similarities and differences. So I can just title it comparisons. What do we notice here? Periods. The green one is 2, the red one is 1. So we notice that the first and the second one have the same amplitude. Okay, so functions 1 and 2 have the same amplitude of 1, right? It's obvious on the graph. What about functions 1 and 3? They have the same period, right? Another similarity, functions 1 and 3 have the same period. Is there a similarity that all 3 functions share? Absolutely, they all start from their individual maximums. Okay, the individual maxima. So functions 1, 2, and 3 start at their maximums. Okay, the maxima. Now let's take a look at another example. So for question number 3, we have to graph y equals tan 1/2 of x. I'm going to include vertical asymptotes in our sketch. Okay, so first of all, to know where the asymptotes are at, we need to express tan using the quotient identity. Okay, so we know that tan x is equal to sine x over cosine x. So cosine basically tells us where the asymptotes of tan is. And we also have to recall that the tan function at something like this, it goes from negative infinity to infinity at every period. All right? Okay, so now since we're looking at tan x, to graph tan 1/2 x, we graph cosine 1/2 x. Now, why do we graph cosine 1/2 x? Because that is the function that tells us the locations of the asymptotes. Anytime the denominator is 0 or cosine 1/2 x has a value of 0, the tan function has a vertical asymptote. Okay, so let's go ahead and graph that. So we have y is equal to cosine 1/2 x. Let's write it in the form that makes it easy for us to determine its components. So we have y is equal to 1 times cosine, factor out 1/2, times x minus 0 plus 0. Okay, now this is easy for us to find the relevant components. Let's find a new origin first. The new origin for our cosine function is 0, 0. Our period is 2 pi over b, and we can clearly see that b is 1/2. So we have 2 pi over 1/2. How do you divide 2 pi by 1/2? We're going to multiply the numerator by the reciprocal of the denominator, which is a fraction. That is the same thing as dividing, okay? So we have 2 pi times 2 over 1. We'll multiply it across. We have 4 pi. That's our period. So this tells us that 4 ticks will be equal to 4 pi. That's our calibration process. Okay, let's see, our amplitude here, although it's not useful for this graph, let's just state it. Our amplitude is the value of A, which is absolute value of A, which is 1. All right, so I'm going to sketch the cosine curve. All that we're doing is just basically using the cosine curve to determine where the asymptotes of our tan, of the related tan curve is located. All right, so that's our max and min. I will take that out momentarily. So that's a max and min. So let's go ahead and do the calibration. How do we calibrate our x-axis? We have 4 ticks. 1, 2, 3, 4 is going to be 4 pi. Okay, going the other direction. 1, 2, 3, 4. That will be negative 4 pi. All right. Now let's put our points for our cosine function. Remember, your cosines looks like the cups. So you start from the maximum for a positive cosine like that, okay? So let's start from the maximum. Center, next tick, center, next tick min, next tick center, next tick max, all right? Going in the other direction, center, minimum, center, max. Now I'm going to draw my cosine function, cosine curve using, you can use a dotted line to draw it. All right, so let's just make it a dotted line. You don't really have to draw your cosine curve because it's just telling us where the asymptotes are at. The only points I care about are the points where cosine has a value of 0. Because when cosine has a value of 0, you have a vertical asymptote for tan. So can you see where the vertical asymptotes are at? They are the roots of the cosine function, right? So here it hits 0. Let's indicate where they are located. We have an asymptote here, 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 and here. Okay, so let's graph the asymptotes. So the first one, second one, let's do that again. Second one, third one, and then we have the fourth asymptote. All right, and then we follow the general pattern that the tan function follows, as we illustrated earlier. It's kind of like it goes from negative infinity up to infinity for every period. So let's sketch what that looks like. So starting from the center, it's going to go to infinity, and then start from negative infinity to the center, from the center to infinity, and then from negative infinity back to the center. That pattern continues forever. Okay? So that's basically what your tan function looks like. From the left-hand side, it goes from negative infinity to the center, and then on the right side, from the center, it goes all the way to infinity, and then this one from the center towards infinity. Okay, so that's the graph. This is a graph of tan of 1/2 x. Okay, let's take a look at another example. All right, it says select the equations that could represent the graph below. Okay, so this is number 4. So this is a trig function that has been phase shifted either to the left or to the right. I want to consider a phase shift to the right here. That's the closest maximum. So let's draw our new y-axis somewhere over here. So the question now is, what kind of function is this? What kind of trig function starts from the maximum and starts to exhibit this periodic behavior? This is your cosine function. Okay, so we know that that's a cosine function. 1, 2, 3, 4, 5. We know the amplitude is 5. It's positive because it starts from the maximum. If it were negative cosine, it will start from the minimum. Now the phase shift is the number of units that it's shifted to the right. Okay, so it had a phase shift here. So the question is, how many units was it shifted to the right? Now let's look at our options. We have 2 possible candidates, either 2 pi over 3 or pi over 3. So what is the accurate phase shift here? Well, it has to be smaller than pi over 2. The only degree measure that's smaller than pi over 2 and bigger than 0 is pi over 3. So our phase shift is pi over 3. Okay? So now we have enough information to write down the first equation of our graph. Is going to be y equals, the amplitude is 5 cosine, 5 cosine. You notice all the options have a period of 1, so let's not bother about that. Let's just focus on the phase shift, x. Now if you shift pi over 3 units to the right, is that a plus or a minus pi over 3? It's you do the opposite, right? So it's minus pi over 3. So you can clearly see that the first option is option letter C. Now, which other candidate could satisfy this equation? Okay, so I told you all in class that I will provide you with an identity that you will use to find another equivalent function with this graph. The co-function identity applicable to this problem is the identity that helps you express a cosine function as a sine function. Okay, so the identity that we're going to use is the co-function identity sine theta plus pi is equal to cosine theta. What does this mean? This means that if you have a sine function and you shifted pi units to the left, what you end up with is a cosine function. Okay? Alright, oh, slight mistake, this is wrong identity. I meant to say negative cosine. Negative cosine. So if you want to express cosine, use a negative cosine, all you do is basically shift the cosine function pi units to the left. Alright? So let me just show you what I'm talking about real quick. So if you have, let's say you have a cosine function, something like this. If you reflect it, it goes like that, and then when you shifted pi units to the left, you end up with what you started with. Alright, so there are a lot of co-function identities, but this is the one that's applicable to this problem. And on the test, I will provide you with the identity. Okay, so you have negative cosine is equal to that. Alright, so this function tells me if I want to express cosine as a negative cosine, I just have to add pi to the angle. Okay, so let's do that here to see the negative cosine equivalent of the result that we got. So it's going to look like this. Y equals negative 5 cosine. Now that I have changed my cosine to negative to compensate for that change, to have exactly the same function that I started with, I need to add pi to my angle. Okay? Alright, so to finish it off, we just put this over 1 times it by 3 top and bottom. And then we have, this becomes negative 5 cosine x minus, let's see, minus pi over 3 minus, let's write it out, minus pi over 3 plus 3 pi over 3. And then your final answer is going to be negative 5 cosine x plus 2 pi over 3. Alright, and we can clearly see that our answer is option letter B. Let's shift our attention to the next question. So it says, which of the following graphs accurately shows y equals negative 2 secant x? So we have 4 asymptotic trig functions, and they have their asymptotes are determined either by sine or cosine. Okay, so let's go over those real quick. The 4 asymptotic trig functions are tan, cotangent, secant, and cosecant. Okay, tangent is given by sine over cosine, which tells us that cosine determines its asymptote. Cotangent is given by cosine over sine. So sine basically determines where the asymptote of cotangent is. Secant is given by 1 over cosine. So cosine determines where its asymptotes are, just like tan. Okay? And then cosecant is 1 over sine. So sine determines where the asymptotes of cosecant is, or are. Alright, now let's take a look at this option right here. The problem tells us that y is equal to negative 2 secant x. So the asymptotes of secant, since we know secant is 1 over cosine, the cosine function helps us to determine where the asymptotes are. But we have to be careful here, there's a negative. Okay, so we're going to be looking at the negative cosine. So what does a negative cosine function look like? Remember, the positive cosine is like a cup opening up, so the negative cosine is like a cup upside down. Alright? So the dotted line represents the function that helps to determine the location of the asymptotes. So if you look at this right here, this dotted line is negative cosine. This dotted line right here is positive cosine. Let's put, this is negative 2 cosine. This is 2 cosine. This dotted line here, you know what it is? It's like an S. This is a negative 2 sine, starting from the center. And this one right here is 2 sine. So which of these accurately helps us determine y equals 2 secant? Since secant, negative secant is dependent on negative cosine, this answer, option A, will be our correct answer because it accurately determines where our asymptotes are at, which is basically the points where negative cosine x hits the x-axis or has a value of 0. Alright, so there you have it. Okay, let's take a look at the next question. We asked to graph y equals tan x plus pi over 2. Alright, so to graph this, we just need to remember what the general appearance of the tan function looks like. Remember the tan, starting from the center, just heads to infinity at the asymptote to the right, and into negative infinity to the asymptote to the left, and exhibits the same behavior forever. Okay? So the function that exhibits that increase in behavior from the left asymptote to the right asymptote are option C or D or B. Okay, let me not circle that. That's not good. So I'm going to eliminate option A. Okay, this could be a cotangent or negative tan. So now we notice that there's a phase shift here, x plus pi over 2. What does that mean? If you have y is equal to tan times x plus pi over 2, what kind of phase shift is this? Plus pi over 2 means you shifted pi over 2 units to the left. Okay, so pi over 2 units shifted to the left in the left direction. Okay, so let's see which of these have engraphed pi over 2 units to the left. If none of them have meets that description, then D will be our final answer. Okay, so pi over 2 units to the left. We have 1, 2, well, we have 1, 2, 3, so this is where pi over 3 is right there in the center. And over here, 1, 2, 3, pi over 3 is right in the center. So which of them fits the description of a tan curve that's shifted pi over 2 units to the left? And we can clearly see that it's option letter C, because this value right here is pi over 2, and we've been shifted pi over 2 units to the left, which is represented by tan of x plus pi over 2. All right, let's take a look at the last question. It says, the graph of y equals cosecant x has the same set of asymptotes as which of the following graphs? So remember, if we express these ones using the appropriate identities, we can know where their asymptotes are located. Okay, so we know that y equals cosecant x can be expressed using the reciprocal identity as 1 over sine x. So if any of these functions has a sign in the denominator, we use a quotient or reciprocal identities, then that will be our correct answer. All right, so option A, y equals secant x is equal to, can be written as 1 over cosine x. Option B, y equals sine x, cannot be expressed using a quotient identity or the reciprocal identity, so we'll leave it alone. Y is equal to cosecant 2x is equal to 1 over sine 2x. And then last but not the least, y is equal to cotangent x is equal to, let's see, what is this again? It's cosine over sine x. Okay? So this one and this one, they both have a sign in the denominator, so we know it can be A or B. But which of them is the correct answer? Notice the original problem calls for there to be sine x in the denominator, but this has sine 2x, which is a problem, but this has sine x, and this is exactly what we want. So we know that option C is not an answer. Your final result is option letter D. This function and this function have exactly the same asymptotes. Okay? They don't look alike, but their asymptotes are identical. Good day, students. In this clip, we're going to be going over 2 examples, reviewing rational expressions. So let's take a look at question number 1. So it says, determine the equations of any vertical asymptotes and the values of x for any holes in the graph of the function f of x equals 6 divided by x squared minus 15x plus 50. So just a real quick reminder of what the holes and the asymptotes are. Remember that the holes or removable discontinuity are the cancelled out factors set equal to 0. Okay? Any factor that you can cancel out from the numerator and the denominator, if you set those factors equal to 0 and solve, the resulting x values are your holes, or removable discontinuities. Okay, and then the vertical asymptotes. Um, so this is point 1, point 2, vertical asymptotes, or you can also call them your infinite discontinuities, or your poles um, are the factors that remain, factors that remain in the denominator set equal to 0. Okay? So when you're canceling out factors, whatever cancels out, you set it equal to 0 and solve. That tells you your holes and your poles. Holes or, I'm sorry, removable discontinuities. But when you're looking for vertical asymptotes, poles or infinite discontinuities, they all mean the same thing. The factors in the denominator that cannot be canceled out, if you set those to 0 and solve, that will be your vertical asymptotes or infinite discontinuity or poles. All right? So let's take a look at the problem under consideration. We have 6 divided by x squared minus 15x plus 50. Now let's factor the denominator. So factor x squared minus 15x plus 50. Okay? You can use the x game to factor this. You can also use a factoring shortcut, but I'm going to do it the long way. So let's, AC goes on top. AC is 50, and B is negative 15. The two numbers that multiply to give you the top and add to give you the bottom. Let's see. How about try negative 10 and negative 5? That works nicely. So we have x squared minus 10x minus 5x plus 50. And if we factor by grouping, take out x minus 10, minus 5, x minus 10. And the factored form is x minus 10 times x minus 5. All right, so our original function f of x in its factored form can be written as 6 divided by x minus 10 times x minus 5. Okay, now let's inspect this to see if we have any holes. Can we cancel out any factors in the numerator and denominator? Is anything common? The answer is no. So we can see that there are no holes in this problem, okay? Or no removable discontinuity. All right, so let's look at the options to see what can be eliminated. We can eliminate C and D because they indicate that there are holes in the problem. Now let's look at A and B. Which one is correct here? So remember, to find your vertical asymptotes, what you do is you set the denominator after it has been reduced to 0 and solve, okay? The factors that remain in the denominator. So all we'll do is we'll set x minus 10 to 0 and x minus 5 to 0 and solve. To solve this, we have x equals 10 and x equals 5. So this tells us that our vertical asymptotes are x equals curly bracket 5 and 10. Those are your vertical asymptotes. So let's look at the options we have here. 10 and 5. Bam, that's the correct answer. Okay, let's take a look at the second question. We're asked to sketch the graph of the function f of x equals 7 divided by x minus 1. So let's go ahead and sketch this. But before we sketch the graph, we have to just remember what the general appearance of a first degree rational looks like. So if we have f of x equals a over bx plus c, the general appearance of this rational function of the first degree, the denominator being of the first degree, is something like this. You have you always have an asymptote. The value of the asymptote is going to be what you get when you solve the denominator. In this case, it's going to be negative c over b. So the asymptote here is x equals negative c over b. So when you're approaching this asymptote from the left, it approaches negative infinity, the function, and then from the right, if you're approaching the asymptote, it shoots up to infinity. Okay, so this is a general appearance of a rational function, the parent rational function, with the denominator being of the first degree. Now, if there are minus here, what happens is that this portion gets reflected to the top, and this portion gets reflected to the bottom. Okay, so this is just for the first degree in the denominator with a constant in the numerator. When the degrees start increasing in the numerator and denominator, then the appearance changes considerably. Okay, all right, so let's look at this. This definitely looks like this. So the main concern here is to look for our vertical asymptotes. So if you look at this function f of x equals 7 over x minus 1, are there any holes or removable discontinuities in this function? Remember the previous problem, we said if you factor out anything and that factor can be eliminated or canceled out from the top and the denominator, then that reduced factor is your holes or removable discontinuity. If you look at this situation, is there anything that can be factored out and canceled out? The answer is no. So the only discontinuity we have is infinite or is a vertical asymptote. So let's look for our vertical asymptote. So to find our vertical asymptote, we're just going to set the denominator x minus 1 equal to 0 and solve. Okay, we have x equals 1. That's a vertical asymptote. We can also call it the infinite discontinuity or our pole. All right, so that exists at x equals 1. Let's go ahead and sketch that line. And from the left, as the function approaches this asymptote from the left, the function tends towards negative infinity. And from the right, this function tends towards infinity, something like this. Okay, so this is just a general sketch. I didn't go into what the end behaviors look like, but this is just a general sketch of what the function looks like at around the asymptotes, the vertical asymptote. All right, so there you have it. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to my channel by clicking here, and also post a comment to let me know what you think. You can give me a thumbs up, I appreciate it. And also feel free to share it with your friends via your respective social networking program. More clips can be found on mathgoodserve.com. Thanks again for watching, and have a wonderful day. Good day, students. In this clip, we're going to be going over some examples reviewing the properties of logarithms. Before we get started, let's take a look at some example, the properties first of all. Remember the product property. If we have log of x, y is the same thing as log of x plus log of y. Okay, and then for the quotient property, log of x over y is equal to log of the numerator minus log of the denominator. Okay, and we have the power property. We have log of x to the a, same thing as you can power down the exponent of the logarithmic argument, log a log of x. Okay, now let's take a look at the first example. The first example says which expression is equivalent to log 16 base 4 plus log 6 base 4 minus log 8 base 4. Okay, so what we're going to do is we're going to condense this logarithmic expression. So here we have a product, we have a sum. Using the product property, this can be converted into a product, and this minus can be converted into a quotient. Okay, so we can rewrite this as log base 4 of 16 times 6 divided by 8. Okay, so we see the plus becomes a times, the minus becomes a division. Okay, let's see if we can reduce this term right here. Let's reduce it. 2 goes here. Let's see if actually we can reduce this by 8. 8 goes here 1, 8 goes here 2, and then just multiply the numerators. That yields log base 4. 6 times 2 is 12. Alright, and then our final answer is clearly option letter A. Alright, let's take a look at the second example. It says if log of 2 is approximately 0.301 and log of 3 is 0.477, then what is the approximate value of log 18? So the question here is, can I express 18 using 2 and 3? So if we think about it, we can express 18 as 18 can be written as 2 times 3, which is 6 times 3. Okay, so now we're gonna write log 18 is equal to log of 2 times 3 times 3. 2 times 3 times 3. Now we're going to use the product property of logarithms to expand this. Okay, so if we apply that here, we have log of 2 plus log of 3 plus log of 3. Alright, now we're going to input the approximate values of each log expression. So this is approximately going to be 0.301. Let's line it up vertically, plus 0.477, and then plus 0.477. Okay, 0, 0, 0. All right, let's add it downwards. So we are going to have 7 plus 7 is 14 plus 1, that's 15, 5 carry 1. 15 again, 5 carry 1. We have 4 plus 4 plus 4, that's 12. 2 carry 1, 1.255. So we see that our answer is option letter A. Alright, let's shift our attention to the third question. So for the third one, we have we get to condense using the properties of logarithms. So we're going to be going backwards in this example. Okay, so here we have the sum, which can be expressed as a product, and then we also have the minus or difference, which can be expressed as a quotient. Okay, so we apply the properties of logarithms here. We have log base 5 of 3 plus. Now this 4 in front, we can use the quotient, the power property to power that 4 up, and then express that term as log base 5 of x to the 4th power minus log base 5 of x plus 2. Alright, now let's go ahead and condense this expression. We're going to have in the numerator log base 5 of 3 times x to the 4th divided by the denominator x plus 2. Okay, So that's basically what our final answer is. Log base 5 of 3x to the 4th divided by x plus 2. Alright, and our final answer is option letter D. Alright, let's take a look at the last example. So for this one, we are to solve this equation. 9 to the 8n minus 11 equals 1 over 6,561. So to do this, the question is, can we express this fraction on the right as a power of 9? Okay, so what we can do is basically go through the powers of 9 using our calculator, or you can do it by hand. So 9 to the first power we know is 9. We know that 9 to the second power is 81. 9 to the third power is 729. And let's see, 9 to the fourth power, 6,561. That's exactly what we want. So we're going to make a substitution here. 9 to the 8n minus 11 equals 1 over 9 to the fourth. It's not complete yet. We want to express this as a power, as 9 to a power, but this is a fraction. So what we're going to do is you're going to use the reciprocal property of exponents to express the right side as 9 to the negative 4. Okay? Now we can just cancel out the bases since they're identical, or we can just take log base 9 of 9 to the 8n minus 11, and then log base 9 of 9 to the negative 4. Okay? Using the inverse property of logarithms, this cancel out, and then these cancel out. You'll be left with, split up our workspace right here. We'll be left with 8n minus 11 equals negative 4. Alright, and let's get n isolated. We'll add 11 to both sides. We have 8n equals positive 7, and then divide both sides by 8, and then you have n equals 7 over 8. So our final answer is option letter C. Okay, so that's that. State which quadratic equation has roots negative 1 and 8. So if two quadratics have the same roots, then in standard form they must be identical. Okay, so we have 6 options. So how about we place all of them in standard form and see which ones are the same. Okay, so we have x squared minus 8 equals negative 7x for option A. To place this in standard form, we'll add 7x to both sides. So the equation is going to be x squared plus 7x minus 8 equals 0. Take a look at option B. We have x squared minus 3x equals 10x minus 8. To place it in standard form, or make it equal to 0, we subtract 10x from both sides and add 8 to both sides too. Okay, so this cancels out, and we're going to have x squared minus 13x minus 13x plus 8 equals 0. Okay, all right, let's take a look at option C. Option C is already in standard form, which is x squared minus 7x minus 8 equals 0. Let's take a look at option D. Option D is 1 minus 8 over x squared equals 7 over x. To place this in standard form, we're just simply going to multiply the entire equation by the LCD of x squared and x, which is x squared. Okay, so we'll multiply through. We're going to have x squared minus 8x squared over x squared. Let's try that again. Minus 8x squared minus 8x squared over x squared equals 7 over x times x squared. All right, so this becomes x squared minus 8 equals 7x, because you subtract exponents. This x cancels one of the x's in the x squared. To put this in standard form, we subtract 7x from both sides. And then we have x squared minus 7x minus 8 equals 0. If you notice, this actually matches with option letter C. So we have two matches right now, C and D. All right, let's take a look at E. We have x squared minus 3x minus 6 equals negative 10x plus 2. To put this in standard form, you simply add 10x to both sides and subtract 2 from both sides. All right, if we do that, we have x squared plus 7x, x squared, let's use a black color. So x squared plus 7x plus minus 8 equals 0. Okay? And then option F matches with option E. It says x squared plus 7x minus 8. Alright, so let's factor, since C and D are the same, how about we factor that first and see what happens? If we get, factor and solve to see if we get negative 1 and 8 as roots. So let's do C using the x game. AC is negative 8, and B is negative 7. So what works here, in the factorization, we can use 1 and 8. Since the sum is negative, the bigger number has to be negative. So we can write this as x squared minus plus x minus 8x minus 8 equals 0. Okay? So we're going to factor that. Let me just draw a barrier here so we don't get confused. Do that again. Okay, so now break it down the center and factor by grouping. Alright, so for the first pair we have x times x plus 1 times x minus, this one is 2 times 2 times 2 times x minus 2 times 2 times 2. From the first pair we can take out x, so we have x times x plus 1. And then here we can take out negative 8, which is 2 times 2 times 2, that's common on both sides of the right side of our partition. And you're left with x. Since you take out a minus, this becomes a plus 1. So the factored form is x plus 1 times x minus 8 equals 0. And then to solve it, you set both of them to 0. Alright, and then the first one is x equals negative 1 if you subtract 1 from both sides. And then the second one is x equals 8 if you add 8 to both sides. So we can see that option C matches the answer. So C and D, since C and D have the same answers or the same equation in standard form, our solution, let's make sure that no other one matches. Let me check A and B to make sure. So A doesn't match, B doesn't match, so it's just C and D. So our answers are solutions. We have two answers here, option C and D. Okay? Alright, let's take a look at the last one, question number 19. So we are to solve the equation. Solve 5x squared t plus 10xt minus 75t. So to do this, we're going to break everything down. So we have 5 times x times t plus 2 times 5 times x times t minus, if you break down 75, 75, you have 5 times 3 times t. So the question is, what's common in all three terms? We have 5 common. So we can factor that out. Take out 5. And then we can also take out x. And actually t. T, and t are common. So we see that 5t is a factor. Alright, we're going to be left with x squared plus 2x minus 15. Okay, so let's factor the inner term in this parenthesis. So make our x So AC goes on the top. AC is negative 15, and B is 2. So what two numbers work? You can use 5 and 3. Since the sum is positive and the product is negative, the smaller number have to be negative, okay? So we have 5t times x squared plus 5t minus 3t minus 15. Break it down to center or factor by grouping. So we have 5t times x. My x is changed into t's. Let me change them back to x's. So 5x minus 3x. All right, so we have x times x plus 5 times x minus 3 times x minus 3 times 5. So from the first two, we can take out x. So we have 5t times x plus 5, and then minus 3, and we're left with x plus 5. So the factored form is 5t times x minus 3 times x plus 5. All right, so our factors are b. We're sure that b is a factor. And then, let's see, do we have x minus 5? X minus 3 is also a factor, so we select D. Now, if you look at 5x minus 15, if I distributed 5 to x minus 3, what will I get? If I distributed 5 to x minus 3, I'll get 5x minus 15. So A is a factor also. Okay? If you notice, A is not in a reduced form. If I reduce A, I'm going to get 5 times x minus 3. So A is a factor also. All right, so there you have it. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel if you haven't already done so. And please feel free to share and post a comments to let me know what you think.